Okay.
Okay, go ahead, Paul.
Okay, so I'm gonna try to go ahead and share my screen. And so you should be able to see this. Okay, so here we go. So what I'm talking about today is the equivariant Lazard ring, in fact, for the cyclic group Z mod P to the N and some applications of that. So I guess what we're talking about is, what do I mean by equivariant Lazard ring? To start with, is actually the coefficient ring, the Z-graded coefficient ring of the equivariant MU, the G equivariant complex cobordism. Let's see if I can find cobordism spectrum, which was originally defined by Tom D. So in fact, I guess I didn't write it down, but on the slide, but of course, one of the central points of non-equivariant stable homotopy theory is that for the non-equivariant complex cobordism spectrum MU, its coefficient ring is the same as the Lazard ring, the ring, a universal ring for formal group laws. And it turns out that's also the case for compact abelian groups. So in the equivariant situation. So that's why I'm calling the MUG star here. Here's my little laser pointer. That's why I'm calling it the equivariant Lazard. So of course, what is the context in which we do equivariant stable homotopy theory is when G is a compact Lie group. But in this talk, what I would like to do is to give an explicit presentation, a calculation of this coefficient ring of MUG in the case when G is a primary cyclic group of order P to the N. And I want to mention two applications of this. One of them is joined with Igor Chris and Yunze Lu, which is that we also computed another MUG star where G is sigma 3, the symmetric group on 3 element. I believe that's the first explicit calculation for a non-abelian group. And then another application we can talk about is in terms of constructing equivariant formal group laws and spectra that corresponds to those equivariant formal group laws, and that work is joined with Chris and Sangben. So I'll try to talk about those two things toward the end. So let me just review a little bit of the previous work on MUG star, the calculation. This is a Z-graded coefficient ring of MUG. So MUG was defined by Tom Deek fairly far back in the 70s, I think. So, or earlier, and then, but there's actually not a lot of explicit calculation on that until recently. So Greenlees and May proved a completion theorem for G abelian. So I'll mention what that means in a moment. Essentially, it's saying that the map from MUG to the Borel cohomology or homotopy fixed point of it is a completion in the coefficients. And around 2000, Chris looked at the G equals to Z mod P case and showed that it is the pullback of a square. And that's actually going to be the starting point of our work. And this work of this pullback square, which I'll say in a little bit more detail in a moment, was generalized by Chris and his student Abram, which is that for G abelian, you can generalize the pullback of a square to a more complicated diagram. Basically, it's in terms of its basically the subgroups of G. So Neil Strickland actually gave a explicit presentation just in the case when G is Z mod 2, and it's basically the algebraic computation that's based on this pullback square that Chris had. And then Dev Singha had a different approach. What he did is that he computed MUT star. So this T here is a torus, or and then that he computed this, and that means that if G is a finite abelian group, you can always write MUG star as, I guess, the co-kernel of a certain map from an appropriate MUT to a self. But this is a less explicit approach, and it depends on some choices. Okay, so let me still, so that's just a very quick review. I'll say some of this in more detail in a moment. So let me go back to the basic background of the Tom Deek's definition of MUG. So we want U to be a complete G universe for a compact Lie group G. So what that means is that it is going to be infinitely, the direct sum of infinitely many copies of the regular representation of the group G. So basically it has infinitely many copies of every irreducible representation. So then the genuine G spectra, that's a basic point of one of the basic points of equivariant stable homotopy theory, is that they're indexed by the finite dimensional representation. So precisely a finite sub-dimensional representation sitting inside the sphere. And so how do we define MUG? How was MUG defined? It's a Tom spectrum of canonical bundles, just like in the non-equivariant situation. So we can take a Grassmannian. So it's inside U, I guess you can put an extra copy of a given finite dimensional V inside of U. And it's just a Grassmannian of the n-dimensional complex bundles, where n is the dimension of V. I guess these are all complex representations. And then, so this has a canonical bundle whose dimension is the same as the dimension of V. So that form, so that's just the Tom space of that is, that's this, what I write here denotes the Tom space of the canonical bundle over the Grassmannian. And this forms G pre-spectral. And MUG is just a spectrification of this pre-spectrum. So this is, so basically it's analogous to the usual non-equivariant definition of MU, but with a, just with inside a complete G unit. And then of course, let me also review the main calculational tool in equivariant stable homotopy theory, which is what's called the Tate diagram. It's due to Greenlees and May. So I'll just write it in a situation, in the simplest situation, where for a group G, there's always a universal contractible free G space, so which we'll call EG. So what we can do is you can take EG plus with a disjoint base point and map it into S naught, just EG goes to one point and the plus goes to the other point. The cofiber EG tilde, so the tilde here denotes the unreduced, the cofiber is just an unreduced suspension of the space, and that's a cofiber. And this cofiber sequence is called the isotropy separation sequence. So then what we can do is that if we have a G equivariant spectrum, so if G is E is a G spectrum, what we can do is just smash this sequence with E. That gives us EG plus smash E to EG tilde smash E. That's a top row of the Tate diagram. Then we can also take the function spectrum from EG plus into E. And then we also can take this function spectrum and smash it with the isotropy separation sequence. That is the bottom row of this Tate diagram. So generally speaking, this FEG plus E is called the Borel cohomology. Its fixed points are called the homotopy fixed points of E. And over here, these two on the left-hand side, EG plus smash E and EG plus smash F from this space into E is actually always an equivalence. So this is called the two of them are called the Borel homology spectrum of E. And their fixed points is called the Borel, I guess, co-fixed points of the homotopy co-fixed points. This term, I guess this upper right corner, I guess I said it's called geometric fixed points, but by that, I really should have said that geometric fixed point is a fixed point of E. And this lower right corner, which has both smash with an unreduced suspension and the function spectrum, is called the Tate cohomology spectrum. So it breaks up this E into more calculable pieces. So what Chris did in the case when E is mu z mod P, and where the group is just the mod P, z mod P, cyclic group of order P, where P is a prime, it's easy to describe what this easy mod P is. We take the reduced regular representation, so a copy of all the non-trivial irreducible representations. We take infinitely many copies of it, and we take the unit sphere in that. That's a good model for easy mod. And if we take the spectrum to be the Z mod P equivariant MU complex cobordism, then what Chris did is to say that MU Z mod P, the Z graded coefficient of MU Z mod P, can be written as a pullback of this square over here. What it is basically this half, the right half of the Tate diagram, and it turns out to be a pullback algebraically on coefficients, and he calculated, well, the three other corners calculated. So what do they look like is that actually the geometric fixed points, which is this upper right corner, has been calculated by Tom Deek. You can basically do it directly by looking at the fixed points on the level of the space of the Tom spaces on the pre-spectrum level. What you have is that you have mu star, that's a coefficient ring of the non-equivariant cobordism spectrum. And then it turns out you have what I'm going to call U alpha. So what is alpha? Alpha is runs from 1 to Z P minus 1. So you can think of it as a element of Z mod P cross. And for E, so E, of course, it's just a cyclic group. So for each one of these elements, there's a non-trivial representation, irreducible representation that's just rotating the complex plane by 2 pi I, by 2 pi over P. So that for the generator of, for 1. So then what we have is that means that for each, so here for the alpha, I'm denoting alpha also as a corresponding representation. So each representation has an Euler class, which we'll call U alpha. So the geometric fixed points, which I mentioned, was done by Tom Deek, really. So it has the Euler class for each U alpha, and it has it's invertible in this in the geometric fixed points. And then in the you also have these elements bi alpha. So I wrote it so that I starts from 1, and there's also, so it's indexed both by a positive integer I and this alpha. You can say that B0 alpha is U alpha. Then the lower left corner, that is the Borel cohomology spectrum. It turns out this will, that's the Greenlees and May's completion theorem that I mentioned earlier, is that this map, downward map, should be a completion at an Euler, at basically the Euler, really all the Euler classes. But as it turns out, all you need to do is to complete at the Euler class of, which I'll just call U, it means U1, where alpha is 1. And it, so that's a Borel cohomology, and it is going to be mu star with adjoined a power series variable U divided by the P series in U. So by P series, what I mean is via the universal formal group law. So here's something else I wrote as notationally. So we know that mu star is a non-equivariant Lazard ring. It has a universal formal group law on it. So the P series of variable x, first of all, x plus fy is just fxy, where f is a universal formal group law. I'll call its coefficients aij's. So these are aij's are elements of the non-equivariant mu star. And the P series is just the x plus f with itself with P copies of f. So it turns out the P series of U, so that's a power series in U, is quotiented out in the Borel cohomology. And then the Tate is basically has both this completion at U, so it's the Borel cohomology, but you invert this U, the Euler class of I guess alpha equals 1. So as it turns out, that actually inverts all of the U alpha because they're multiples of each other. So and this map, vertical map, that's the important part of Fritz's calculation is where do these BI alphas go? Is that BI alpha goes to, you take a formal coefficient, x plus f, and then the alpha series, alpha number copies of U added plus itself via this universal formal group law on mu star. So then, so this is a power series in x and u, and you just take the part that has xi, where x has exponent I. So in other words, if you can also write it out in terms of the coefficients of the universal formal. Okay, so so this is so basically our 3 other corners of this thing are calculated, and so what Strickland did is algebraically calculate the pullback for when G is Z mod 2. So here's a theorem that's due to Strickland that gives an explicit calculation of the Z mod 2 equivariant mu. It has I guess I should mention has generators as a mu star algebra. Maybe I should in fact add that. Say as mu star algebra. So so it has, what kind of generators does it have? It has a set of generators Bij's where ij's are greater than or equal to 0, but in fact B00 is actually just a U here. And then you have another set of generators QJs where J is greater than or equal to 0. It has this set of relations. So I guess in this case, of course, only alpha is 1. There's only one non-trivial element of Z mod 2. So you don't have this superscript alpha here. So B01 is 1. B0J is 0 for every bigger J. Bij minus Aij. So remember, Aij is a constant. It's an element of mu star, which is a coefficient of the formal group law. Then once you do Bij minus Aij, you can divide it once by U, and that quotient is Bi comma J plus. So there's, for each I, there's a series of Bi, sequence of Bij. Q0 is 0. And Qj minus an element Cj. So what is Cj? You take the 2 series in U and call, just Cj is just notation for its coefficients. So that's also an element, that's just an element also in mu star. So for each Qj, you subtract the Cj, subtract this mu star element, and you can divide it by U once, and you get the next Q. So there's one extra sequence of generators Q. So notice that C0 is 0 because a 2 series does not have a constant term. C0 is 0. So when J is 0, this relationship just gives you Q1U is 0. So U in particular is a 0 divisor here. And in fact, it's annihilated precisely by this Q. Okay, so that's a statement of Strickland's theorem for calculation for mu Z mod 2 star. And how you should think about it is that you should take, again, this map, the map from the mu Z mod 2 star to the Borel cohomology, which just looks like mu adjoined a power series variable U divided by the 2 series. So where does the Bij's come from? They correspond in this, and this will turn out to be the completion of, well, as we already, well, this is the completion at U of mu Z mod 2 star by the completion theorem of Greenlees and May. So, so you take X plus FU, so just where X is, again, a formal variable. So this notation means that you take only the part where the exponent of U is J or more. So you get rid of all the, you throw away all the terms where U has a lower power than J. Then, so once you have this, you can divide by Uj. That is, and also fix the power of X to be I. So that's going to be a power series in U, and that is what Bij corresponds to down here. And that's where the relation, this Bij minus Aij, you can divide by U, is just precisely saying that if you take this power series over here, and then divide by Uj, this has a constant term once you divide by Uj, which is precisely, the constant term is precisely Aij. So that means you can subtract the constant term from this Bij, then you're allowed to divide by U one more time, and what you get is precisely Bi comma J plus 1. And what about the Q's? It turns out you also need a extra sequence of generators. So, which is just a follow. You take the 2 series in U. So, and then again, this notation, the absolute value of U greater than or equal to J here just means you take only the term where U has at least J power. So that means divided by J, that's a power series. So in particular, Q0 is the actual 2 series, which is 0 in this ring, which is a Borel cohomology. And so each time, again, the constant term of this power series is precisely the Cj. So if you peel that off, throw that away, you can divide the power series by U again. That gives you a different power series here, and that is a generator in MU Z mod 2 star. So this is a story in due to Strickland for the case when you have MU Z mod 2 star, when G is Z mod 2. So the first thing I did is to generalize this story to G equals to Z mod P case. So here's my first theorem, which is that MU Z mod P star, the coefficient ring of MU Z mod P, has the following generators. So again, this is as a MU star algebra. You have that Bij alpha. So you don't just have one set of Bij's, but you have they're also indexed by alpha, which runs from 1 to P minus 1, basically the non-trivial representations of the group. We'll write B00 alpha to be U alpha. That is the Euler class corresponding to alpha. Qj is, you have a set of Qj's where J is greater than or equal to 0. That's the same as what Strickland had. So back here, you have these Qj's. But there's one more thing, one more new family of elements, which is lambda alpha. Alpha runs from 1 to P minus. That's not a series. There's only one of them for each alpha. So what are our relations is that you first have some relations which are similar to the Z mod 2 case. You have B01, 1 is 1. When alpha is the 1 is 1. B0 J alpha, when alpha J is 0. When alpha is 1 is 0. When J is greater than or equal to 2. That's only true for the case when alpha is 1. You don't have these when alpha is some other element of non-trivial element of Z mod. We have Bij alpha minus a different constant, which I'll call Aij alpha. Then you can divide, actually you can just divide by the basic U, which is U1. And then you get the next element in this sequence, which I'll call Bi, and J increases by 1, and still for this particular alpha. So the Aij alphas are, you take X plus over F with the alpha series on U. So U, again, remember that U is U1. So, and the coefficients are what I call Aij alpha. Okay, the relations involving Q are similar to the Z mod 2 case. Q0 is 0, Qj minus Cj. So in this case, the Cj's are now the coefficients of the P series on U. So Qj minus Cj, we can divide by one copy of U, and then you can get the next generator, Qj plus 1. But these lambdas aren't, well, you don't see them for the Z mod 2 case. That's what makes it more complicated. A lambda 1 is 1. That's why you don't see it in the Z mod case, because all you have is only alpha is 1 for Z mod 2. And lambda alpha times B01 alpha. So remember, that's not 1 if alpha is not 1. 1 in Z mod P is going to be 1 plus a integer times Q1. So we still, from here, we still have Q1 times U is 0. So this K alpha Q1 is a 0 divisor. So these two things, lambda alpha, you should think of as an approximate inverse to B01 alpha. So K alpha is an integer. You actually have some choices, but a sort of canonical choice is that you take alpha inverse in Z mod P and think of it in Z, then alpha times alpha inverse is 1 plus a multiple of P if you're looking at things in Z, and you can take that as your K alpha. So where does this come from is that the guide is, again, you want to look at the completion map from MU Z mod P to its Borel cohomology. So remember that left vertical map increases square. So what we have is that goes now to MU adjoint U divided, modded out by the power series, the P series in U. So Bij, again, goes to the, we take X plus over F, but now, I think I made a mistake here. Let's roll this. This is an alpha series in U, not the opposite. Alpha is a number. Correct this real quick. It's alpha U. And again, we can take, we can peel off take only the parts where the terms where the U has power at least J that allows us to divide Uj, and you take only the ones terms where X has exponent exactly I. So that lands in here. So Bij alpha corresponds to this element of mu star U over P series. So again, the relationship comes from the fact the constant term of this power series is precisely our Aij alpha. Remember, Aij alpha are the coefficients of this guy, X plus F alpha U. So you can peel off, you can subtract the constant term and divide it. And then Qj's, Q0 is actually the P corresponds to the P series in here, which is 0. So Q0 is 0. That's our relation that we had over here. And then, so Qj goes to the part of the P series where U had in U, where U has power at least J and divide by Uj. So again, this Qj corresponds to the series in here in the Borel cohomology with constant term Cj. That's why Qj minus Cj we can divide by U once. So in particular, the U alphas, the Euler classes just goes to the alpha series on U. What are these B01 alphas? Why are they special? Is that they go to the alpha series in U divided by U. So that exists because this the alpha series doesn't have a constant. What about these lambda alphas? They also have to be there. It turns out they're kind of a fake inverse for B01 alpha, which is, so it's, I said it's kind of a fake U over alpha. So why is that? Is that in the numerator, because P of U is modded out, you can take 1 plus a constant multiple of P, an integer multiple of P, this number series on U. So that's alpha inverse, which is just means a number between 1 and P minus 1, apply to alpha of U. So that means you can divide it by alpha of U. So, but it's in and of itself is not an actual inverse to this element. Among other things, its constant term is not necessary. It's not 1 if alpha is not 1. Its constant term is the inverse of alpha in Z mod. So, but what you do get from this, it's they multiply together to 1 up to a 0 divisor. But once you multiply by a U alpha, you do get lambda alpha times U alpha is U. And if you do U times B01 alpha, which is it's a fake inverse, it is U alpha. So all the Euler classes are multiples of each other. In particular, that means if we invert U, we invert all of them. And if we complete at U, we complete all of them. So that's in fact where the proof comes from. It's just basically similar to, it's basically our algebras, and it is analogous to what Strickland did, which is that you have a standard result from commutative algebra, which says that if you have an element with bounded torsion, then you go to, if you invert U and complete at U, and then the original ring is a pullback. So you just check that, let's go back all the way to the Chris theorem. You check that for the ring that's described in the generators and relations, that in the statement of the theorem, if you invert at U, you precisely get this thing, the geometric fixed point. And if you complete at U, you precisely get the Borel cohomology. So, and then you also have to check that it has bounded torsion. In fact, its annihilator of all its powers is Q. Okay, so that's the ZMAT P story. I guess one thing I want to mention is that this this ring has a natural ZMAT, has a canonical ZMAT P cross action, namely because it has a ZMAT P cross action on all the other 3 corners, because where U goes to the alpha series on U down here, and it permutes the U alphas in the geometric fixed. Okay, let me talk a little bit about MU ZMAT P star as what does it look like? It's obviously a deeply non-Noetherian ring. So the way you can think about it is that let me give you 2 other rings. One of them is still looks like the Borel cohomology, MU star adjoined U, but you divide out by PU, the P series over U. And then over here, you take U alpha, BI alphas. You don't need the U alpha inverses. You do need the lambda alpha, and you don't want to put the Q's there because Q's 0 is 0, so it doesn't need to be added extra. With the relation that Q alpha, U alpha is, again, there's a slight typo here. I meant U. Is U1. So there is the map, a map that goes down from this, which is basically, let me still look. This map over here, that's kind of the main thing that we have. And it, let me go find the thing. So then on the algebraic geometry spec of these rings, I can take the point, the principal ideal generated by U in here, and look at the point that's its image over here. I guess that's why I needed to divide mod out by PU over U to make sure that U is a regular element. Otherwise, in the Borel cohomology itself, U is a 0 divisor. So what we do is that you can take the spec of R and blow it up at this point I, that's basically the pre-image of U on the ring level. So that means the spec of S actually can lift to here, map to here into this. And you take, well, you actually probably should take image of the spec of the image of this map. Let me call that will turn out to be affine. It's spec of R1, a new ring called R1. So I have this diagram over here. And this spec R1 is this blow up is the model for peeling off the constant term and divide by U1. That's going to give you all the BI1 alpha and the Q1. And then you can take this R1 and again map it into S, do the same thing. So you repeat this process infinitely many times. This infinite repeated blow up gives us a model for MU Z mod stuff. Okay, I'm kind of running out of time, running behind a little bit. So let me tell you that there's also a G to the Z mod P to the N case. And the way to deal with this is to look at a staircase diagram where you have MU Z mod P to the N. And we can look at for various Z mod P to the R's. So here you have Z mod P to the N tilde smash this MU Z mod P to the N. Here you would have E, the tilde of E, but for Z mod P to the N minus 1, and so on until you get to EZ mod P tilde. And the way you should think about these is that the Z mod P to the R's you should think of as a quotient group of Z mod P to the N, and you can also say they're E of a family of subgroups not containing, it's actually not containing Z mod P to the N plus R plus 1. And down here, so these are kind of on the top row, you get these partial geometric fixed points of this Z mod P to the N spectrum. And the general philosophy is that that's always inverting a U P to the R, the Euler class of the representation corresponding to P to the R. And as you move along, if you're inverting more and more, so you're inverting these with higher and higher values of R. And downwards, you first do the function spectrum from EZ mod P to the N into this spectrum. And then next one will be F from EZ mod P to the N minus 1 plus into the MUZ mod P to the N, so on. All the way down here, you should get F EZ mod PM plus just again, an error. MU Z mod P to the N. And in this case, the general principle is when you go to Borel, these are partial Borel cohomologies. And what they do is that you complete at UPRs, and as you go down, the value of R decreases. So it turns out the diagram, the square that you really want to use is this one, the top wide square. So now let me just give you the statement, which is that MU Z mod P to the N has the same collection of generators, Bij alphas, lambda alpha. You have these sort of N minus 1 levels of Qs. And the relations actually get kind of more difficult. So you write alpha to be L times P to the R plus S, which is alpha P to the, and also gamma P to the T. So where gamma P is 1. So what that means, the P to the T is the highest power of P that divides a number alpha, which is in a non-zero element in this group, Z mod P to the N. And P to the R is actually the biggest power of P that's less or equal to alpha. So then if your alpha is an actual power of P, then B01 is 1, B0J is 0 if J is greater than 2. And for each Bij alpha, you cannot subtract a simple element constant anymore. Rather, what you're subtracting is a polynomial that depends on this L, and it's what's plugged into this polynomial are actually finitely many of the B, K, S's. So K is the one that varies. S is this number. It's a polynomial in these generators, which, and then once you have that, you can divide by UPR. That's basically sort of the biggest U that can be divided if you subtract something from Bij alpha, and then you get the next element. So the Q's, QR0 is not 0 anymore. It's the UPR plus 1. It's sort of the U for one higher power of P. You can say UPN is a 0. Then you can still peel off the CJ. That's still the coefficient of the P series. And then you can divide by UPR. Now, lambda is 1 if your alpha is a power of P. Lambda alpha, not B01 alpha, but a slightly different element, which can be defined recursively in terms of the B01 alphas, is 1 plus this integer times this thing, which is, this is also a 0 divisor. It times, if you multiply UPT to it, this term becomes 0. So again, lambda alpha is an approximate inverse to this underlying B01 alpha. That's not quite the B01 alpha itself, because the B01 alpha, you're actually peeling off more. So, but I'm actually only have about 2 or 3 minutes left. So in this case, I'm not going to go through the guide here, but rather I want to talk about a quick application. Is that this jointly with Chris and Lou, we actually also calculated mu sigma 3, which is the sigma 3 is the symmetric group of 3 elements. And that's, I think, the first calculation for a non-abelian group. So sigma 3 just has 2 non-trivial representation. You still have a sign representation. There's an irreducible 2-dimensional real representation that rotates by 2 pi over 3. So easy mod 2 plus is actually the sphere of infinitely many copies of alpha plus. Easy mod 3 is sphere of infinitely many copies of gamma plus. So we're going to take the Tate diagram, but just with easy mod 2 plus, and it turns out, I'll just give you the answer, is that mu sigma 3 star is a pullback on the algebraic level of this 5-term diagram, where this is actually the mu z mod 2 star. This is mu, just a non-equivariant mu star. This is mu z mod 3 star, but fixed points with the multiplicative group of z mod 3, which is z mod 2. And these 2 rings are described. You have the with U gamma and U gamma inverse, and then the B gammas, but only with the even i's divided by 2. And R is a ring that has both U gammas and U gamma inverse. So it's basically geometric fixed point with respect to gamma, but you still have the usual your U alphas, which is respect to the sign representation. So so basically I guess you're still working with the representations, the Euler classes of the representation. So I guess the proof of this theorem is basically, it's just a bunch of working. So you basically take these two terms each and turn them into, and each of them, you have its own pullback diagram for this corner and also for the Borel one, and putting all these together. Let me go back to the statement of the theorem. It's all a bunch of yoga with these pullback squares. And so you get this 5 terms. And then I think I don't really have time for talking about equivariant formal group law. So let me just say equivariant formal group law is something, it's a formal group scheme over a commutative ring with a choice of parameters. So in terms of ring, it means it has a complete half algebra. It has a choice of parameters. And I'm actually not going to be able to say all this, but the point is that actually it was proven by Hausmann. Hanke and Wimler showed that MUG star for GZ-mod2 is actually the Lazard, the universal ring for formal group laws for G's equal to Z-mod2. Hausmann actually showed it for all abelian compact Lie groups. Chris and Lu has another proof, and jointly with Chris and Somberg, we constructed various examples of equivariant formal group laws realized by complex-oriented spectra, and some of them are done by finding a ring and defining precisely a map from your MU-Z-mod-P star into that ring. So I had some slides on this one, but I didn't get a chance. For example, if you have a ring like this, where G is just Z-mod2, I can define a map from MU-Z-mod2 into this ring, which actually gives you a Z2 equivariant formal group law. It's a deformation of the equivariant multiplicative formal group law, but it's not equivariantly multiplicative. And we also constructed a Z2 equivariant spectrum with this formal group law. And we have other cases, but this is a very simplest set. Okay, so that's all I'll say for today.
Right, great. Thank you very much, Paul. Let's thank Paul for the very impressive talk. Very interesting. Thank you. Yeah, your computational power is really impressive. You know, it's maybe I should say overwhelming. Are there any questions? Since I have to go, I may step in first and ask a question. You computed the equivariant mu in the case of the non-abelian group sigma D by basically presenting it as an extension of two abelian groups.
Yes. Yes.
I mean, is there? If you want to address the case of a more general case of a non-abelian group, do you anticipate doing the same, or?
Well, I think it will probably be somewhat more complicated. For example, I think I haven't been working on this. I think Chris's student Lu has done some, is doing some work on that. Basically, I would guess the things that the most next step would be the dihedral groups.
Mm-hmm.
But I think that already has more representations. So, but it is an extension of two things. So maybe you could do something like this in this case.
Mm-hmm. Yeah, it seems like the representation ring of a group should play a role.
Yes, absolutely. It's basically because you see that it's the sort of you start with these Euler classes of all these representations. In this case, you have U gamma and U alpha, and you have this sort of blow up story, this sort of peeling off the constant term, and you can always divide by U by the appropriate basic representation, Euler class. Again, that's how you get these sequences of things. So that's how you get these. So it seems very definitely you have to start with the Euler classes of all these.
Mm-hmm. Very good.
Sorry, I didn't have chance to probably spend much time at the beginning, but this is this R, this corner here, is explicitly calculated and generated.
Yeah, I see.
Well, I just have a comment. I think you're saying the next step to compute for the dihedral case. I think the quaternion group, which is case might be also interesting.
Could be, that could very well be the case. I haven't thought about that, but you're right, that could be interesting.
That might have what interesting in low dimensional topology. Yeah. Quaternion group, because the subgroup of pin 2.
Okay, yeah, that's
yeah.
a good point.
Thanks.
Other questions? All right. Well, actually, I'm planning to make available the recording of this talk and also the slides that Paul agreed to send to me. I haven't done.
Okay, I will send the slides. So let me stop the sharing.
Yeah, and also, what did I want to say? Yeah, it's still not ready. The web page is not ready for doing this, but I'm working on it with Tyler. Tyler also has the page. Yeah, also Craig Westerland apologized that he wouldn't be able to be here personally for your talk, but he was very happy to know that you agreed for the recording and sharing the slides. Yeah.
Yes.
So thank you very much, Paul. Again, let's thank Paul, who again for a wonderful talk. And
thank you for inviting me.
Yeah, sure, sometime soon.
Thank you.
Yeah, thank you. Bye-bye.
Bye.
I'm stopping the recording.
Okay.
Let's see.